For problem number 1, we'll be doing optimization here, and we see that Mary's Fudge sells square-bottom tin containers of holiday fudge. The size and bottom of the tin costs $1 per square inch, but the special lid costs $1.50 per square inch. So we have a container that we know is a square-bottomed, three-dimensional container, and we have two things that we know about it. We know how much the sides cost, and we also have the next sentence, which is she would like to sell her fudge in a cubic inch size container. So that means we have the volume. So we have two things. We have volume and we have cost. So like in every optimization problem, you're going to need to take the derivative of one of these and set it equal to 0 in order to minimize or maximize that quantity. And we'll use the other equation to substitute and make sure that we only have one variable. So in this case, we want the dimensions that will minimize cost. So we know we're going to be taking the derivative of cost and we're going to be setting it equal to 0. So we just need the equations here and then we'll start to substitute. So we know that this is a three-dimensional container and it's square-bottomed. So if you were to think about what that would look like, we have a 3D box here that is the container. And we have dimensions of it that we don't know, but we know that the bottom is square. So if the bottom is square, that means its two dimensions have to be equal. So if we call one x, the other one is still x as well because it has to be a square bottom. The height may or may not be the same, so we'll call that y. So we have an x by y box. So our volume is those three things multiplied together, which would give us x squared times y. So there's our volume equation, and we know that that's equal to 80, given to us in the problem. So now let's come up with a cost equation, because that's what we're going to have to minimize. So all the sides and the bottom cost $1 per square inch, but the lid is $1.50. So the cost of each face is going to be its area times the cost per square inch. So for all of the sides and the bottom, that's 1. And for the top, that's 1.5, 150. So let's break this up because all of the sides are the same. Every side of this box, its area is x times y. We have 4 of those, so we would have 4x times y. Furthermore, their costs are all $1, so we would just be multiplying it by 1. So the cost of all the sides is just 4xy. Now let's think about the other sides, the top and bottom. Both the top and the bottom have areas of x squared because their dimensions would be x times x. The bottom costs $1, but the top costs $1.50. So we would have 1x plus 1.5x, or x squared on both of those. So we'd have 2.5 x squared. Again, we have two sides of x squared, but they cost different amounts. So we're multiplying the bottom one, x squared, by 1. We're multiplying the top one by 1.5. So here's our volume equation. Here's our cost equation. We're trying to minimize cost, so we're going to have to take the derivative of this and set it equal to 0. The problem is that we have two variables, x and y. We need it to be in one variable to really do that. But that's where we can use this that I've underlined. The volume is x squared y, and we know that's equal to 80, so we can make an easy substitution. If we divide over by x squared, we can see that y is equal to 80 divided by x squared. And we're going to use that to sub in here, and then we'll only have one variable. So our cost equation becomes 4x times this substitution. One of those x's would cancel, and we'd be left with 320 divided by x. 4 times 80 is 320. We'd still have the 2.5x squared. Now our cost equation only has x, and now we can solve the problem. We're trying to minimize the cost, so we want to take the derivative of this. So we want c prime. This is 320x to the minus 1, so that would give us negative 320 over x squared when we do the derivative. Here we just use our power rule, multiply by 2, so that would be 5x. So we want this to be 0 in order to give us our minimum. So what we're going to do is now solve for x. So I'll add the 320 over x squared to the other side. If we multiply over the x squared and divide by 5, we would get that x cubed is equal to 64. 320 divided by 5 would give us 64. X cubed equals 64 only has one solution, which is x equals 4. So since that's our only answer and we were trying to minimize, it's safe to assume that that is our minimum and it's not accidentally a maximum or something. If you had multiple answers, you'd have to see which one is the min and which one is the max. So our minimum cost occurs when our x is equal to 4. Remember, x was one of the dimensions of this box. So the problem is asking us what are all the dimensions so that the cost is minimized. Well, we know that the bottom should be 4 by 4. And to find out the height of the box, all we need to do is plug it right back into our volume equation that we have very concrete. If x is equal to 4, 4 squared is 16. 16 times 5 is 80. So that means that y has to be 5. So therefore, if x is 4 and y is 5, the size of our box that makes the cost the smallest is 4 by 4 by 5, where 5 is the height. That shape box gives us a volume of 80 with the lowest cost.
The Teaching Center, UF's Learning Resource Center.